Welcome to Module 2 of Programming and Analysis, Programming and Requirements. This module is about understanding the problem before you design the solution. Buildings fail when architects skip this step. Sites flood, programs miss the mark, zoning blocks construction, and owners end up with the wrong building on the wrong site. NCARB dedicates 33 to 40% of the entire PA exam to this one module. So if you're going to invest your study time wisely, this is exactly where to focus. We've got 24 slides across 6 sections, and I want to give you a quick roadmap so you know what's coming. Section 2.1 covers programming fundamentals, Pena's problem-seeking, process, program document. Section 2.2 covers space and area analysis, net versus gross, efficiency ratios, room data sheets, standards. Section 2.3 covers spatial organization, adjacency, circulation, stacking, blocking, zoning. Section 2.4 covers stakeholder engagement, identification, methods, consensus, conflict resolution. Section 2.5 covers owner requirements and criteria, OPR, functional versus aesthetic, performance criteria, codes. Section 2.6 covers feasibility and existing conditions, feasibility studies, adaptive reuse, needs assessment. Here's the thing, each section builds on the one before it. By the end, you'll see how these 6 areas connect and why a mistake in one area can quickly snowball into problems across all the others. So with that, let's jump into Section 2.1, Programming Fundamentals. The building works perfectly for a use the client never needed. Programming errors don't show up in construction, they show up in occupancy. A hospital with undersized emergency departments. A school with inadequate egress for its actual enrollment. A courthouse with no secure circulation for prisoners. These failures trace back to one cause. The architect solved the wrong problem because they never properly defined the right one. The ARE exists to protect the public. Programming and requirements failures harm the public in very direct ways. The table on screen connects programming failures to real public harm. When occupant loads are underestimated, the egress system is designed for the wrong capacity. That's a life safety crisis during an emergency. When functional adjacencies are ignored, patients in hospital emergency rooms are too far from trauma bays, and outcomes suffer. These aren't design failures, they're programming failures. The building was built correctly to the wrong specifications. NCARB tests this because defining the right problem is the architect's first duty to the public. Here's the key insight. Programming is where the architect acts as the public's advocate, translating vague wishes into measurable requirements that ensure the building will be safe, functional, and appropriate. NCARB tests programming because a building that solves the wrong problem is a building that fails the public, no matter how well it's designed. Here is the single most important distinction you need to understand for the ARE. Programming is about defining the problem. Design is about solving it. These are fundamentally different activities, and confusing them is one of the most common mistakes on the exam. This table draws the most important distinction on the entire PA exam. Programming is analysis, taking the problem apart to understand it. Design is synthesis, putting a solution together. Programming asks what? Design asks how. If you remember nothing else, remember this. Programming precedes design, and mixing them together is the fastest way to build the wrong building. The exam will present scenarios where someone is designing during programming, and the correct answer is always to stop and finish defining the problem first. Here's the key insight. William Pena said it best. Don't state a solution as a problem. If someone says, "We need a bigger lobby," that is a solution statement. The problem might be visitors cannot efficiently find their destination upon arrival. Programming identifies the real problem. Design provides the solution. Why does NCARB care? Because an architect who jumps straight to design without proper programming will design the wrong building. They will solve a problem that does not exist while ignoring the one that does. Programming protects the public by ensuring the building actually meets real needs. William Pena's Problem Seeking is the foundational text for architectural programming and the framework NCARB expects you to know. It organizes all programming information into a simple but powerful matrix. Pena's problem-seeking matrix organizes all programming information into 4 categories that you need to know cold. Goals capture what the client wants to achieve, their mission and vision. Facts document existing conditions like site data, user counts, and budgets. Concepts explore organizational strategies and functional relationships. And needs quantify the requirements, square footages, adjacencies, and equipment. Each category is then examined through function, form, economy, and time, creating a comprehensive 16-cell framework. Each of these 4 categories is then examined through 4 considerations: function, form, economy, and time. This creates a 4x4 matrix, 16 cells, that organizes the entire programming effort. The 4 considerations on screen expand each programming category into specific lines of inquiry. Function asks how the building will be used and what activities occur. Form considers the site and physical constraints. Economy addresses budget, operating costs, and lifecycle costs. And time covers schedule, future changes, and phasing. Together with the 4 categories, these create Pena's complete programming framework. The exam loves testing whether you can place a specific question into the right cell of this matrix. Here's the key insight. The exam loves to test whether you can distinguish between goals, qualitative aspirations, and needs, quantitative requirements. Create a welcoming environment is a goal. Provide a 2,000 SF lobby with seating for 30 is a need. Goals guide design intent. Needs drive the space program. Programming is not a single event. It is a structured process with distinct phases, each building on the last. Skip a phase, and the entire program is compromised. The 5-step programming process on screen moves from abstract to concrete. You start by establishing goals with stakeholders, understanding their mission and vision. Then, you collect facts about existing conditions and precedents. Next, you uncover concepts like organizational strategies and priority systems. Then, you determine quantitative needs, the actual space program. And finally, you synthesize everything into a clear problem statement. The exam tests this sequence, and the key trap is that programming is iterative within these steps, but should never jump to design solutions. A critical warning: common exam trap. The programming process is not linear and rigid. It is iterative. You cycle back through steps as new information emerges. However, you should not be designing during programming. Iteration within programming is expected. Jumping to design solutions is not. The final output is the architectural program document, which becomes the basis for design. It should be comprehensive, organized, and agreed upon by all stakeholders before design begins. The architectural program document is the deliverable that concludes the programming phase. It is the bridge between programming and design, and it serves as a reference throughout the entire project. The program document contents on screen show what the final deliverable actually looks like. It starts with an executive summary and project goals, then moves through existing conditions analysis, the detailed space program, adjacency requirements, technical needs, code analysis, budget framework, and project schedule. This document becomes the reference throughout the entire project. It's not a one-time deliverable. The exam tests whether you understand that the program document bridges programming and design and must be formally approved by the owner before design begins. April 2026 Exam Update. Starting April 27, 2026, PA Objective 4.5 changes from Develop a project budget and schedule to Review and assess the feasibility of the project budget and schedule to meet the project scope. You no longer need to create budgets from scratch. Focus on reviewing estimates prepared by others and assessing whether they are feasible for the project scope. Here's the key insight. The program document is a living reference, not a one-time deliverable. It should be revisited and updated as the project evolves. However, major changes to the program during design should trigger a formal review process, often involving additional stakeholder engagement and potential fee adjustments. If you remember nothing else about space programming, remember this. Net area is the space people actually use. Gross area is everything including walls, corridors, mechanical rooms, and structure. The ratio between them determines whether a building is efficient or wasteful. The area definitions on screen establish three critical terms. Net assignable area is the space people actually use: offices, classrooms, patient rooms. Departmental gross adds the internal circulation and walls within a department. And building gross includes everything within the exterior walls, all the mechanical rooms, stairs, elevators, and restrooms that make a building function. Understanding these three levels is essential because the program deals in net area, but the building is built and budgeted in gross area. These three formulas on screen are among the most commonly tested calculations on the PA exam. Efficiency ratio equals net divided by gross. It tells you what percentage of the building is usable space. Grossing factor equals gross divided by net. It's the multiplier you apply to convert a program into a building size. And gross area equals net area times the grossing factor. Getting the direction wrong, dividing when you should multiply, or vice versa, is the #1 calculation mistake on the exam. Here's the key insight. The grossing factor is one of the most commonly tested concepts. If a program calls for 50,000 NSF and the building type typically has a 1.5 grossing factor, the building needs to be 75,000 GSF. Getting this wrong means either a building that cannot fit the program or one that is unnecessarily expensive. Different building types have dramatically different efficiency ratios, and the ARE expects you to know the general ranges. A hospital is far less efficient than an office building because it requires more circulation, mechanical space, and specialized infrastructure. The efficiency ratio is one of the single most commonly tested concepts on PA. Expect at least one question about it on exam day. Why does this matter? Because programming drives the gross building size, and gross building size drives cost. A 50,000 NSF hospital program becomes a 100,000 GSF building, 50% efficient. The same program in an office building becomes 62,500 GSF, 80% efficient. The difference? 37,500 CESFIF is tens of millions of dollars. Getting the efficiency ratio right at programming is the highest leverage cost decision in pre-design. Here's a memory device. Hospitals, labs, courthouses equals half efficient, from mixedly 50 to 60%. Schools equals 60 to 70%. Residential, offices equals 80 to 85%. Retail equals 90%. The more specialized circulation and infrastructure a building type needs, the less efficient it is. The efficiency ratios table is one you should study until the ranges feel intuitive. Commercial offices run 80 to 85% efficient. Most of the building is usable space. Schools drop to 60 to 70% because of wide corridors, gymnasiums, and cafeterias. Hospitals and laboratories are the least efficient at 50 to 60% because they need massive mechanical systems, wide corridors for bed transport, and specialized infrastructure. The grossing factor tells you how much building you need. A hospital program at 55% efficiency requires nearly twice the net area in gross building. A critical warning: never memorize exact numbers for the exam. Understand the ranges and, more importantly, why certain building types are more or less efficient. The exam will test your reasoning, not your ability to recite a specific percentage. A room data sheet is the detailed specification for an individual space. Think of the space program as the table of contents and room data sheets as the chapters. Together, they tell the full story of what the building must contain. Room data sheets are the DNA of the space program, and the table on screen shows the 9 categories each sheet documents. Identification pins down the room's name, number, and department. Area specifies net square footage and ceiling height. Environmental requirements cover temperature, humidity, acoustics, and lighting. Equipment lists everything from fixed casework to technology infrastructure. And code requirements capture occupancy classification and egress needs. These sheets are created during programming but used throughout the entire project lifecycle, from design through construction verification. Here's the key insight. Room data sheets are created during programming but used throughout the entire project. They inform design, guide specifications, and serve as a checklist during construction. When a room data sheet says STC 55 between patient rooms, that requirement flows through to wall type selection, detail drawings, and construction verification. Space standards provide starting points for programming. They represent industry consensus on how much space typical functions require. While every project is unique, standards prevent you from programming a 50 censifuv conference room for 12 people. The space standards on screen give you industry benchmarks for common room types. Executive offices typically range from 200 to 350 square feet. Standard private offices run 120 to 180. Open workstations have shrunk dramatically and now range from 48 to 80 square feet per person. Conference rooms need 25 to 30 square feet per person, and hospital patient rooms run 250 to 350 square feet, according to FGI guidelines. Parking deserves a careful split. A standard parking stall by itself is roughly 165 to 200 square feet, a 9 by 18 to 9 by 22 footprint. But once you allocate the drive aisle and circulation that the stall actually depends on, the figure jumps to about 300 to 400 square feet per space, with 325 to 350 as a common planning number. These are starting points that must be adjusted for each project's specific needs. Modern workplace trends are pushing open workstation sizes down from 80 plus SSF to under 50 SSF per person, while increasing shared and collaboration space. The ARE may test your understanding of these evolving standards. A critical warning: space standards are starting points, not mandates. A programmer must adjust standards based on the specific client needs, user activities, equipment requirements, and organizational culture uncovered during stakeholder engagement. Building area calculations are where all your programming data comes together into a single number. How big does this building need to be? Getting this wrong means either a building that cannot house the program or a budget that cannot build the building. The area calculation process on screen shows the 6 steps from individual room areas to total building size. You start by listing all program spaces with their net areas, then subtotal by department. Here's where it gets tricky. You apply a departmental grossing factor to add internal circulation within each department. Then sum all departments. Then apply a building grossing factor to add major circulation, mechanical, restrooms, and structure. There are two levels of grossing, departmental and building, and the exam will test whether you apply both correctly. Here's the key insight. There are two levels of grossing. Departmental adds internal circulation within a department, and building adds major circulation, mechanical rooms, restrooms, stairs, elevators, and wall thickness. A common exam mistake is applying only one grossing factor when both are needed. Adjacency analysis determines which spaces need to be near each other, which should be separated, and what kind of connection they require. This is the bridge between a list of rooms and an actual building layout. The adjacency analysis tools on screen progress from data collection to spatial exploration. The adjacency matrix is a systematic grid that documents the relationship between every pair of spaces. It's the most rigorous programming tool. Bubble diagrams translate that matrix data into spatial concepts using circles and connecting lines. Stacking diagrams show vertical organization across floors for multi-story buildings. And blocking diagrams approximate space allocation on a floor plan. The exam tests which tool belongs to programming versus design. Matrices and stacking diagrams are programming tools, while blocking diagrams bridge into design. The adjacency rating scale on screen uses a 5-point system that the exam tests directly. Essential adjacency means shared wall or direct door connection. Think operating room to pre-op recovery. Desirable means nearby with a short walk acceptable. Admin offices near conference rooms. Neutral means no spatial relationship. Undesirable means these spaces should be separated. Loading docks away from the main entry. And prohibited means these must never be adjacent. A hospital morgue must never be next to patient rooms. The exam loves asking what essential adjacency actually means in practice. Here's the key insight. The adjacency matrix is a programming tool. Bubble diagrams, stacking diagrams, and blocking diagrams are transitional tools that bridge programming and design. The exam will test whether you know the difference and when each is used. Circulation is the space that gets people, materials, and equipment from one place to another. It is invisible in the space program, but can consume 25 to 40% of the building. Failing to account for it properly is one of the most common programming errors. The circulation types table defines 4 levels of movement space in a building. Primary circulation includes the main public corridors and lobbies that everyone uses. Secondary circulation serves departments internally, the hallways within an office suite. Tertiary circulation is the movement space within individual rooms, aisle space around desks and furniture. And vertical circulation moves people between floors through stairs, elevators, and ramps. Understanding these levels matters because they're accounted for differently in the grossing factors. The circulation efficiency percentages on screen explain why certain building types are so much less efficient than others. Office buildings use only 15 to 20% of their area for circulation because the corridor layouts are simple. Hospitals consume 30 to 40% because they need separate paths for patients, staff, visitors, and materials. Courthouses need 30 to 35% for the same reason. Judges, public, and detainees each need their own path. When the exam asks why hospitals have low efficiency ratios, circulation is the primary answer. A critical warning. Some building types require separate circulation systems for different user groups. Hospitals need distinct paths for patients, staff, visitors, and materials. Courthouses need separate paths for judges, public, and detainees. This dramatically increases the building gross area. Once you know what spaces you need and how they relate to each other, you must organize them vertically, stacking, and horizontally, blocking, while considering access zones, zoning. This is the final step of programming before design begins. The stacking and blocking principles on screen are the organizational rules that govern three-dimensional building layout. Public spaces belong at grade level, where visitors can find them. Major mechanical goes at the top or in the basement to keep it out of prime real estate. Heavy loads like labs and archives should be near grade for structural efficiency. Related departments stay adjacent both vertically and horizontally. And service access must be separated from public entry. These principles inform the program before design begins, establishing constraints that the designer must respect. The Zoning Concepts Table organizes building spaces into 5 access levels. Public zones are open to all visitors without escort: lobbies, cafeterias, retail. Semi-public zones require check-in, waiting rooms, and reception areas. Private zones are staff-only spaces, like office areas and break rooms. Restricted zones have limited access even among staff: server rooms, pharmacies, evidence storage. And service zones handle building operations, mechanical rooms, loading docks, maintenance. The front-of-house versus back-of-house separation is a fundamental programming decision that must be established before design. Here's the key insight. Front of house, public-facing, and back of house, staff or service, is a fundamental zoning concept. Every building has this division. The exam often tests whether you understand that separating these zones is a programming decision that must be established before design begins. A stakeholder is anyone who is affected by or can affect the project. Miss a key stakeholder during programming, and you will discover their requirements during construction, when changes cost 10x more. The ARE tests your ability to identify and prioritize stakeholders. The Stakeholder Categories table identifies 6 groups that contribute different types of information to the program. The owner provides budget, schedule, and decision authority. End users contribute functional requirements and workflow needs. They know how the building will actually be used. Operations and maintenance staff contribute durability and maintainability requirements that designers often overlook. Community stakeholders bring context sensitivity and aesthetic expectations. Regulatory stakeholders define code and zoning constraints. And the project team brings technical feasibility and cost reality. Missing any one group during programming creates blind spots that surface expensively later. Here's the key insight. The owner is not always the user. A developer building speculative office space has very different goals than the tenants who will occupy it. A school board has different priorities than the teachers and students. Programming must capture requirements from both owners and users and reconcile the differences. The method you choose for stakeholder engagement depends on who you are engaging, how many people are involved, and what kind of information you need. The ARE expects you to match the right method to the right situation. The Engagement Methods table matches 8 techniques to different stakeholder situations. One-on-one interviews work best for key decision-makers who need deep engagement. Focus groups of 6 to 12 people capture shared concerns within user groups. Surveys reach large populations with quantitative data. Workshops bring cross-functional groups together for problem solving. Design charrettes provide intensive collaborative design input, though they blur the programming design boundary. Town halls handle community engagement for large groups. Site visits reveal behavioral patterns, and post-occupancy evaluations learn from completed projects to improve future programming. A critical warning: a design charrette is not pure programming. It blurs the programming or design boundary by bringing stakeholders into a collaborative design exploration. The ARE may test whether you understand that charrettes happen at the transition between programming and design, not during early programming. Gathering stakeholder input is only half the job. The other half is documenting it clearly, resolving conflicts, and gaining formal consensus. Without documented consensus, programming decisions get relitigated during design, wasting time and money. The Documentation Best Practices table covers 5 essentials that prevent programming decisions from being relitigated during design. Meeting minutes distributed within 48 hours capture decisions while memories are fresh. A decision log with dates, participants, and rationale creates accountability. Sign-off on program sections provides formal acknowledgement. Visual documentation reduces ambiguity in written descriptions, and priority rankings by stakeholder group make trade-off decisions transparent. Without documented consensus, every programming decision becomes subject to second-guessing during design, wasting time and money. Here's the key insight. The architect's role in stakeholder engagement is to facilitate, not dictate. You are the expert in translating user needs into spatial requirements, but you are not the expert on the user's actual needs. Listen first, translate second, and always confirm your translation with the stakeholders. Conflicting stakeholder needs are not a failure of programming. They are the normal condition. The marketing department wants open, collaborative space. The accounting department wants private offices. The budget cannot afford both. The programmer must facilitate resolution. The Conflict Resolution Strategies table presents 5 approaches for when stakeholders disagree, which is the normal condition, not a failure. Priority ranking forces choices when budget is limited, using categories like must-have, should-have, and nice-to-have. Phased implementation resolves conflicts through time. Build the core now and expand later. Shared resources satisfy multiple groups without duplicating spaces. Design innovation finds creative solutions that satisfy competing requirements. And when all else fails, the decision escalates to the owner with clear options and documented trade-offs. The exam consistently tests that the owner, not the architect, makes the final call. A critical warning. The architect should never unilaterally resolve stakeholder conflicts. The architect presents options, documents trade-offs, and facilitates discussion. The owner makes the final decision. If the exam asks who resolves a programming conflict, the answer is almost always the owner, with the architect's guidance. The Owner's Project Requirements, OPR, is a formal document that captures the owner's vision, goals, and requirements for the project. It originated in the commissioning world, ASHRAE Guideline 0, but has become essential to the programming process. The OPR is the benchmark against which the entire project is measured, from schematic design all the way through post-occupancy verification. Every major design decision later in the project gets traced back to the OPR. Does this choice meet the owner's stated requirements? If yes, proceed. If no, either the design is wrong or the OPR needs to be updated with owner approval. Projects without an OPR drift. Individual design decisions made in isolation. No single standard to measure against, and nobody can say whether the final building actually met the owner's intent. Here's a memory device. OPR equals owner says what they want. BOD equals design team says how they'll deliver it. Commissioning equals independent verification the building actually performs. 3 documents, 1 continuous accountability chain from programming through occupancy. The OPR contents table shows 8 sections that together form the benchmark for the entire project. Project description establishes the basics: type, size, location. Owner's goals capture business objectives and sustainability targets. Functional requirements define space needs and adjacencies. Performance criteria set measurable targets for energy, indoor environment, and durability. Budget constraints establish financial boundaries. Schedule requirements pin down milestones. Sustainability goals may include LEED targets or net zero aspirations. And technology requirements cover everything from IT infrastructure to building automation. The OPR drives design decisions. Every major choice should trace back to it. Here's the key insight. The OPR is developed during programming and drives the entire project. The basis of design, BOD, is the design team's response to the OPR, showing how design decisions meet the owner's requirements. OPR equals what the owner wants. BOD equals how the design team will deliver it. The exam loves this distinction. Programming focuses primarily on functional requirements because they are quantifiable and testable. Aesthetic requirements exist but are handled differently. Understanding this distinction is critical for the ARE. The functional versus aesthetic requirements comparison on screen clarifies a critical programming distinction. Functional requirements like 12 air changes per hour, a conference room that seats 20, or a server room maintaining 68 to 72 degrees are quantitative, testable, and verifiable. Aesthetic requirements like conveying innovation, feeling warm and welcoming, or complementing a historic district are qualitative and subjective. Both are valid, but on the exam, when a question asks about programming, the answer almost always relates to functional requirements. Aesthetic goals are captured during programming, but addressed during design. Functional requirements can be verified objectively. Either the room is 250 sesfethered or it is not. Aesthetic requirements are subjective and require ongoing dialogue between architect and client. Both are valid, but they are documented and tracked differently. Here's the key insight. On the ARE, when a question asks about programming, the answer almost always relates to functional requirements. Aesthetic goals are captured during programming, but addressed during design. If the question is about what to document in the program, focus on measurable, testable criteria. Performance criteria establish measurable targets that the building must meet. Some come from the owner, energy use targets, some from codes, minimum ventilation rates, and some from industry standards, FGI guidelines for healthcare. Programming must capture all of them. The performance criteria categories on screen cover 7 dimensions that the program must document. Structural criteria include floor load capacity and vibration limits. Thermal criteria set indoor temperature ranges and energy use intensity targets. Lighting criteria specify illumination levels and daylight goals. Acoustic criteria define STC ratings and background noise levels. Indoor air quality criteria set ventilation rates from ASHRAE 62.1. Durability criteria address material life cycle and maintenance frequency, and accessibility criteria go beyond ADA minimum compliance to include universal design goals. The key concept is that code requirements set the minimum, but the owner's OPR may establish higher targets. A critical warning: code requirements are the minimum. Programming may establish performance criteria that exceed codes based on the owner's goals. For example, code may require ASHRAE 62.1 minimum ventilation, but the owner's OPR may target enhanced ventilation for a LEED credit. The program must document both the minimum, code, and the target, owner goal. Programming does not happen in a regulatory vacuum. Zoning, building codes, and other regulations establish constraints that directly affect what can be built, how big it can be, and what it can contain. A programmer who ignores regulations will produce a program that cannot be built. The Regulatory Factors table shows 8 types of regulations that constrain the program before design even begins. Zoning determines whether the proposed use is allowed and how big the building can be. Building code classifies the occupancy and sets fire safety requirements. ADA requires accessible routes, restroom quantities, and space clearances. Fire code may require separation distances and sprinkler systems. Environmental regulations impose wetland setbacks and stormwater management, and historic preservation may restrict changes to existing structures. A programmer who ignores these constraints will produce a program that cannot be built, which is why the exam tests regulatory awareness during programming. Here's the key insight. Floor area ratio, FAR, is one of the most commonly tested zoning concepts. FAR equals total floor area or site area. If a site is 20,000 SF and the FAR is 2.0, the maximum building area is 40,000 SF. This is a programming constraint because it caps the building size regardless of the programmatic need. Before committing to a project, smart owners and smart architects conduct feasibility studies to determine whether the project is viable. Feasibility is not one question, but several, and each must be answered before proceeding. The Feasibility Studies table defines 6 dimensions that must all pass before a project should proceed. Physical feasibility asks whether the site can support the building. Financial feasibility asks whether the owner can afford it. Regulatory feasibility asks whether authorities will allow it. Market feasibility asks whether there's demand. Operational feasibility asks whether the owner can maintain it. And schedule feasibility asks whether it can be built in time. The exam's favorite trap is presenting a project that passes 2 or 3 dimensions and asking if it's feasible. The answer is always no until all relevant dimensions are satisfied. Here's the key insight. A feasibility study is not advocacy. The architect's role is to provide honest, objective analysis, even if the conclusion is, this project should not proceed. Telling an owner their dream project is not feasible is uncomfortable, but essential. The ARE values objectivity over optimism. Not every project starts with a blank site. Existing facility assessments evaluate current buildings to determine whether renovation, addition, or adaptive reuse is viable. These assessments are critical pre-design activities that inform the go, no-go decision. The existing facility assessment components cover 7 evaluation areas for renovation and adaptive reuse projects. Structural assessment determines whether the building can support new uses or additional floors. MEP assessment evaluates the age and adaptability of mechanical, electrical, and plumbing systems. Building envelope evaluation checks roof condition, wall integrity, and moisture issues. Code compliance identifies current deficiencies and the upgrades that new construction or change of use would trigger. Hazardous materials assessment looks for asbestos, lead paint, and other contamination. Historic significance evaluation determines tax credit potential. And space utilization analysis reveals how well current spaces serve their functions. The Adaptive Reuse Decision Factors table helps determine whether renovation or new construction makes more sense. Sound structure with adequate capacity favors reuse. Generous floor-to-floor heights that can accommodate modern MEP systems favor reuse. Good building envelope condition favors reuse. But extensive contamination, low floor heights that restrict modern systems, or declining locations all favor new construction. Historic tax credits can tip the financial balance toward reuse. The exam tests this analysis framework. Adaptive reuse isn't always the answer, even though sustainability trends favor it. Here's the key insight. Adaptive reuse is increasingly important as sustainability concerns grow. The greenest building is the one already built, but the exam will test your understanding that adaptive reuse is not always the right answer. Sometimes the cost of bringing an existing building to modern standards exceeds new construction. Needs assessments and master planning take the widest view of an owner's requirements. They look not just at a single building, but at an organization's total facility needs over time. These are strategic, long-range planning activities. The needs assessment versus master plan comparison clarifies 2 pre-design activities that sound similar but serve different purposes. A needs assessment asks, what do we need? It's a gap analysis that identifies where current facilities fall short of organizational requirements. A master plan asks, how do we get there? It provides a 10 to 25-year physical implementation strategy with phasing and capital planning. needs assessments focus on organizational requirements, while master plans focus on physical campus implementation. On the exam, master planning is always positioned as a pre-design activity that establishes the framework for individual building projects. Master planning is the most comprehensive pre-design activity. It considers not just buildings, but site infrastructure, transportation, open space, utilities, and phasing over decades. Individual building programs must align with the master plan. Here's the key insight. On the ARE, master planning is always presented as a pre-design activity, not a design activity. A master plan establishes the framework for individual building projects. Each building project then has its own programming, design, and construction phases. The master plan is the umbrella. Individual projects are sheltered beneath it. Let's bring it all together. You've just worked through the entire foundational layer of Programming and Analysis Module 2, Programming and Requirements. That's a lot of material, so let's recap what you've learned and why it matters. Section 2.1, Programming. Pena's 5-step method separates problem from solution. Programming defines, design solves. Section 2.2, Space and Area. Net is usable. Gross includes walls. Efficiency ratio drives cost per net square foot. Section 2.3, Organization. Adjacency matrix first, stacking second. Circulation eats 10 to 25% of gross area. Section 2.4, Stakeholders. Engagement methods scale with complexity. Silent stakeholders become project killers. Section 2.5, OPR. OPR is the legal foundation of design. Performance criteria bind outcomes, not methods. Section 2.6, Feasibility. Feasibility studies find showstoppers early. Adaptive reuse tests the shell before the program. The thread connecting all of these sections is this. Programming and analysis isn't about designing. It's about understanding the site, the program, and the constraints before you design. Get this right, and every design decision that follows gets easier. Your next step is the Foundational Check quiz. Don't worry if you don't get every question right the first time. The quiz is a learning tool, and the explanations will help strengthen any areas where you're less confident. Once you're through it, you'll be ready to move into advanced concepts. You've built a solid foundation. Time to put it to the test.